Alright, so this is my attempt number 2 at making you a Chapter 5 practice sheet, looking at the thermodynamic energy analysis equation. And the practice sheet that I handed out in class, we're going to practice questions 1, 2, and 3 on this video, and then I will do math question 4 and 5 and 8 on a second video. So looking at question 1, calculate the total heat transfer for 48 hours through a brick garage 3 inches thick. And I give you the R value of that. That measures 15 feet by 20 feet with a heating on at 65 degrees Fahrenheit with 20 degree Fahrenheit outside. So we're going to have an equation, and the equation that we're going to use is the QC over time is equal to 1 divided by its R value. That's times the area times the change in temperature. And I've actually already laid out the equation, so I have my equation up above here, and then I have all my factors. So I have the R value, which is 0.4 per inch, the time 48 hours, the change in temperature of 65 to 20 being the outdoor temperature in the area, 15 by 20 feet. First step I have to do is change my R value, because we have to account for all of the R value sets, and that's 3 inches of garage. So the first step I need to is take my 0.4 and times that by 3 inches of garage and get my new R value number and my actual R value of 1.2. And because this is an R value, it's an evaluation of feet squared over an hour in a degree Fahrenheit over a BTU. So that's my unit. Now that I have that, I can pretty much place everything into my equation, and I'm going to change my set of 15 by 20 to the area of 300 feet squared. So I'm going to actually do that, and I'm also going to subtract my 65 by 20 and get my 45 degrees in my building so that I can just plug everything in the equation. So I'm going to do 1 divided by my 1.2, and that's feet squared, hours, degrees Fahrenheit over BTU, and this is all times the area of 300 feet squared times my change in temperature of 45 degrees Fahrenheit. And we also are looking for a time of 48 hours, so I'm going to take my T and move it to this side of the equation, making it a times it, which is 48 hours in the day. And that's going to give me my total answer. So first I'm going to just cross out my units. So feet squared, hours to hours, Fahrenheit to Fahrenheit, and my answer is going to be left in BTUs. Remember to do the 1 divided by the 1.2 first, and then times all your other numbers. And when I come out with 540,000. So 540,000, and that is the unit of a BTU. So that's the amount of energy lost over the course of 48 hours with the temperature change of 65 inside the building and 20 degrees Fahrenheit outside the building for question 1. Alright, so let's take a look at question 2. Alright, so question number 2, calculate the difference between storm windows with an R value of 1.72 and a single pane with an R value of 1.26 for a 3 feet by 4 feet squared out window in a location of a 5,000 degree day. And there's also a part A on this, and it asks for the average cost of energy is 95 cents per kilowatt. What is the savings between the storm window and the single pane? Which would be best to install? And so we're going to take a look at working on this problem. So I actually wrote out my equation up above. I'm going to use the Q is equal to the sum of all 1 over R's times the areas times the 24 hours in a day times the degree day, and I put in my single pane window to my double pane. I already times my 3 times 4, giving me 12 feet squared, and my degree day of 5,000. And we're going to actually do the equation twice, one for single pane, one for double pane, and then subtract to find the difference. Okay, so I wrote down everything for the single pane window, and I've got one that's going to be divided by 1.26, and that's in units of feet squared, hours, degrees Fahrenheit over BTU, times 12 feet squared, times 24 hours in a day, times 5,000, and that is degrees Fahrenheit day in a year. As we play this, we're going to take out feet, hours, degrees, and days over here with days over here. And all I'm left with is BTUs in a year. And I'm going to do 1 divided by the 1.26 first, and then the 12, the 24, and the 5,000. And I come up with and I'm going to round and just leave it as 0.14 because I'm rounding. And that's BTUs in a year. And that's for my single pane. And now I'm going to write out the problem for double pane. And I'm just going to write this number up here for single pane windows so that we remember it, so that we know what to do with part A of question 2. Alright, so laying out this next part to the question, I have 1 divided by 1.72, and I'm going to take care of the units first. So feet squared crosses out, hours crosses out, degrees Fahrenheit crosses out, and days and days crosses out, and I'm going to get BTUs in a year. And so I do 1 divided by 1.72, that times 12 times 24 times 5,000, and I end up getting 837,209.3, and I rounded upwards, but it comes out to be 0, and that's BTUs in a year. And so I'm going to write that up here. 209.3, and that's BTUs year. Now the next step is to subtract these two numbers from one another to get the difference. And then when I get the difference, I can then work with the kilowatt hours. So I'm going to find the difference, and then I'm going to change it to a kilowatt hour. Alright, so I'm subtracting my single pane window above from my double pane window, and this is the number I get here. But in order to solve for the 95 cents in a kilowatt hour, I have to switch this whole thing over to kilowatt hours. So I look up on my table and I find that 1 kilowatt hour is equal to 3,413 BTUs, British thermal units. So I'm going to divide my British thermal unit of 3.41 or 3,413, sorry, 3,413, and that's a BTU over 1 kilowatt hour. So BTUs are going to cross out, and I'm going to get kilowatts in a year. Alright, and I divide the 3,413 into the 305,647.84, and I end up with 89.55, and that's kilowatt hours in a year on my layout. Now for the next part, I have to do the money amount, and so the money amount is 95 cents because that's what you'd be paying in electricity according to part A of problem 2. So I do 89.55, that's kilowatt hours, times the 0.95, and that's cents per kilowatt hour in a year. So kilowatt, this is over a year. Kilowatts is going to cross out, and I'll get a money amount over the course of a year. And I end up with 85.0, and it's 7.6, so I'm going to round up to make it 8 cents. And so each window, if I had a 12-foot square window, each window that I would replace, I can save $85.08 each year. let's say the windows cost me $500, because we can play this game and take it a step farther, and I can do 500 divided by the 85. And I can get 5.8 years. So the window savings in energy costs will pay back in 5.8 years. And then after that 5.8 years, everything else is just money in the bank on my savings for electricity. So every year I basically save $85 per year.